Hello, this is my first video on forces and bodies, and it's intended to be an introduction to how the whole thing works. So here's a car driving along a motorway. How do we calculate the motion of the car? Well, we're going to have to understand a lot of new terms about forces, about having simplified models of this car and how to create force diagrams. And then we're going to put all that together and use Newton's laws to do our calculations of acceleration. So first up, we need to think about some new terms. First term is force. Well, the OED says that a force is an influence on a body that tends to change its motion. And what's a body? Well, a body's a physical structure. In this case, it's the car. So there we are. We're off and running with some ideas. Our next thing we need to do is start thinking about this car. Well, the car's accelerating because of the force of the engine. And it's being held back by air resistance and road friction, but that's quite a complicated situation, isn't it? Because we could think about, the engine, how the engine's working, etc. But actually we need to keep it simple. So let's have a look at a very much first step simplification of the diagram. So first thing we've got an engine force, haven't we? Now we could spend time talking about the pistons and the powertrain and all that sort of thing, and it would all get really complicated. So actually what we want is just a very simple idea that we've got an arrow pointing forward, which is the force, ultimate force of the engine. Yes, that's what's driving us forward. And what's holding us back? Well, we've got air resistance. Yeah, we've got pressure all over the surfaces of our car, but actually we just want to say there's one big lump of air resistance. So we're going to treat that as a single force. And then we've got 4 tyres, and they're in contact with the ground, and fronts and backs of them are operating in different ways in terms of load, but ultimately there's some frictional force holding us back, isn't it? That would try and slow us up. So there's our first idea. We've reduced this to 3 forces, and that's going to get us going. Second thing we want to do is simplify it a bit further. We've got this big lump of something that's a car. Well, actually, we're going to treat this as a single point, a particle, Is it reasonable to do that? Yeah, it's reasonable to do that as long as our car's not rotating. Because if it was rotating, we'd have energy going into the rotation if it was spinning around or rolling about or something. But actually it isn't, it's just going forward. So there's no energy going into that. All of this force is being used to drive it forward. So I'm going to treat that as a single body here, usually shown as a circle. So what have we got to now? We've brought this down to effectively a single particle here in the middle with a force pulling us forward or pushing us forward, the engine force, and we got 2 forces holding us back, air resistance and road friction. But that's quite a simple model now, isn't it? That's something we can work with. So what we've created here, and this is the last part of it, is we're starting to create our force diagram. There's one other thing we need in our force diagram. We've got our forces on it. We also need to know something about acceleration. So here we've got another smaller arrow with a double arrow head on it, and you can see here that we've got A for acceleration, and you'll see that's in lowercase. All of the others, forces are in uppercase on our force diagrams, the acceleration is in lowercase. So you can easily see what's a force from what's the acceleration. And what we're going to do now, well, we could from this diagram try and work out what the resultant force is that's driving us forward by looking at the arrows and looking at, we're interested in the direction of our acceleration. So say if I had an engine force of 60 newtons and I had a air resistance of 15 newtons and friction on the road of 10 newtons. So I've got 60 newtons pushing us forward. I've got 25 newtons holding us back. So overall, we would have a force driving us forward of our 60 minus 25. So we would have 35 newtons driving us forward. That would be the resultant force. We could just do that, couldn't we? Because it's just an adding and subtracting business, isn't it? So if I've generalized that more, I would see that that resultant force is my engine force driving us forward, take away the resistive forces, so the air resistance and the road friction force, holding us back. So we've created our resultant force. Once we know our resultant force, we can use that with Newton's second law. Now, Newton's second law says force equals mass times acceleration, and we've therefore got to do that calculation, and we've got to decide the direction we're doing the calculation. Well, if our acceleration is to the right here, which we saw above with our double arrow, then we're going to treat our Newton's second law as operating in that direction. Yeah. So on the left hand side, we've got our force in that direction. Well, we worked that out just now as our resultant force. There it is. And our acceleration, which is mass times acceleration in that direction. Yeah. So everything's going left to right. Quite often in these sort of diagrams, everything's moving left to right. So here we are. We could actually see what acceleration is here by just rearranging the formula below. But in principle, we've gone through and simplified our model, and now we've worked out what our acceleration would be. So to summarize, we've looked at the fact that there's a concept of a force, which is an influence on a body tending to change its motion, the body itself, which is a physical structure. Previous videos, we looked at the idea of acceleration in our CVAT videos, etc., which is the rate of change of velocity. Here we've applied Newton's second law, which says that force typically is equal to mass times acceleration, i.e. force is proportional to acceleration. We've also here done some important simplifications. We've simplified the forces down into 3 basic forces, and we've treated the body as a particle. In effect, we're saying that forces act in the centre of mass. We've created our force diagram here, where we've shown all our forces with large arrows, and all the forces are named in capital letters. And then we've got the acceleration here, which is a double headed arrow, and the acceleration is usually shown in lowercase. We've then applied Newton's law in the direction of the acceleration, and we've come up with we calculated our resultant force, and we made that equal to the mass times acceleration. So there we go. That's our basic concept that we're going to apply to every problem that we deal with from now on. Have fun.